There we go. Hey, James. Okay, so let's start off by constructing some instances that show something is decidable, and as we do this, let's learn what decidability even means. Okay, so what have we said so far? What does decidable 2 divides 4 mean?
It's possible for the computer to decide that 2 divides.
Yeah, so this is just you've got to remember with 2 divides 4 is just a prop, so it might be some arbitrarily difficult proposition, it might be the Riemann hypothesis, and decidable is a way of expressing that we have an algorithm to decide whether that proposition really is true or really is false. So decidable is implemented in a very, very simple way. Decidable is just the following inductive type, parameterized by a proposition. There are 2 constructors of decidable P. One of them is called is false, and you need to give it a proof that P is false. And the other one is true, and you need to give it a proof that P is true. Okay? So the only way to ever have an instance of decidable something is if you've got a proof that it's either true or false. So how are we going to construct the instance of 2 divides 4 is decidable?
Is it just to show that it's true? Yeah.
We're just going to show that it's true. Yeah, so we might, since we're building an inductive data type, we might use the constructor that we want. So we could write decidable dot is true, and now our goal has changed from showing that 2 divides 4 is decidable to showing that 2 divides 4. Okay, so that seems pretty sensible. How do you show that 2 divides 4? Did people do things like this when getting started on question 5, the old question 5? Yeah, okay. Let's be lazy for now so we can get on with things. Maybe we'll come back in a moment. Norm num is a nice tactic for doing lots of boring arithmetic that humans shouldn't have to do. And indeed, norm num happens to know, oh, I should have compiled before I came. It's going away and compiling stuff about the real numbers because norm num is meant to work with reals as well. Okay. Anyway, for now, let's...
So before in the assignment you've said, like...
Yeah.
So is mathlib, like...
Yeah, so norm num is part of mathlib.
It's part of mathlib.
Yep.
Okay, yeah.
Basically, if you have to write an import statement, you're probably using mathlib.
Okay.
Yeah, okay, but so let's maybe do this one with let's maybe sorry, this just hasn't compiled because it says it's red because it still hasn't been compiled mathlib. What a pain. Sorry, hopefully it'll catch up. Maybe let's, for now, just comment that out and let's do things by hand. How would we do it by hand? So, a calc block. Ooh.
To like have P 2 by 2 equals 4.
Yeah, well, maybe, yeah, so I liked Martin's suggestion that we just should look under the hood at what division actually means, which is some existential statement. And at that point, you know how to proceed, because at this point, we just need to provide the C. So what's the tactic name to
Use 2.
Yeah, use 2 is great. Unknown identifier use. And that's in mathlib.
Exact.
Well, exact actually won't quite work either, because exact would be saying that we'd actually be providing both the C and the proof of that property of C. We could, I guess, use refine Oh, okay, and that worked. So refine is something where is like exact, but you're allowed to have placeholders in it, some underscores, and so that then now gives us the proof obligation 4 equals 2 times 2. How do you prove that one? Yeah, ruffle is probably good. Great. Okay, so we could give an honest proof of decidability there. Actually, much harder. Is when you need to do this. So how do we do this one? Maybe let's import norm num for a moment. Yep. And then norm num will finish it from there. But we can okay. If you wanted to do it another way, you have to work a little bit harder to do divisibility by hand. Okay. So decidability of individual propositions is all fine. Things catch up here. It did. Maybe. But oh, there we go. Okay. So more often, what you'll find is that you need to provide an instance of decidable pred. So decidable pred is a predicate which just says you've got some type alpha and you've got some function from alpha to type, and then decidable pred R is just asserting that for every A in alpha, R of A is decidable. Okay, so it's just a whole family of decidability statements. So the sort of example that you might have there, say we define evenness of natural numbers in the obvious way. Oops, that needs a colon equals. And then we might want to provide an instance of, that says that this is a decidable predicate on the natural numbers. And now life gets a little bit harder. We have to prove an infinite family of decidability results at this point. So what do we do? This is getting closer to obviously deciding the question about decidable pred prime, but it's a baby case of primeness. Just deciding.
Can be decided if it's either true or false. So you've got to do both.
Yeah, well, I mean, we're actually going to have to look at the point is now that because we're defining a decidability for a predicate, we're actually going to have to look at the argument n, and in some cases do things. So how about we start with a lambda n comma, and then the goal inside here becomes just the decidable pred even turns into decidability of the evenness of n. Okay, but how are we going to do this? We can't just use the sort of norm num trick or the refine trick that we had before, because those somehow relied on us actually having a explicit numerical value for n. We were just doing arithmetic with actual numbers. We have to.
Can you show that AB is equivalent to like n mod 2 is? Or is that just moving it over?
Yeah, that so yeah, so this is maybe a good thing. So maybe we could define another version of evenness that says that what n mod 2 equals 0. Okay, and maybe we could, let's imagine that we had we already had decidability of this other guy. In fact, maybe mathlib can just give us one. Oh, no, not quite. Okay. Oh, a little bit surprised. Why didn't? I was hoping that was going to work. Does anyone see what I'm doing wrong? I'm just trying to unfold the definition of even prime.
If you make it a lemma, and then you can do something.
Oh! Oh, I see, because the point is there's no argument yet. Okay, great. Great, okay. Then once there's an explicit argument, it unfolds, and then, look at that. There's a fantastic tactic, apply instance, which goes away and asks Lean's type class mechanism to find us an instance, and it actually magically manages to do that for us. So we okay. So in a moment, maybe we'll look at what apply instance was actually doing, but let's just imagine for a moment that we had that. So we've got the decidability of even prime, and maybe we've got a lemma, even if and only if even prime, which says that for every natural number, those are the same. And let's imagine that we've proved that. You'd expect now that there's a way of proving decidability of the other version. Okay, if one statement is a decidable predicate, but it's equivalent to the other one, we should be able to move across. How on earth are we going to get something like this? Well, so we can maybe make a guess about where this might come from, because we want to see if we can guess it just by typing.
Using the lemma and then apply instance does it.
Yeah. Oh, okay. What I wanted to do was to let's see if we can find it. Let's search everywhere. Maybe decidable of if and only if. Oh, there we go. Okay, so decidable of if and only if was a lucky guess, maybe. So there's a few different things that's fine. Let's go look up some of them and see if see what they say. So I just jumped to some random occurrence of this definition and then jumped to its definition. So what does this one say? Ah, okay, this one actually looks pretty good. There's two versions of it, I guess, that go in different directions, but this says that if you've got an instance of decidable A, you can get an instance of decidable B from an if and only if. Okay, so maybe we could just use that one. So decidable of if and only if, and now we can, if and only if we want to hand it, is that. Lean complains that the arguments weren't quite right. The first argument was meant to be a proposition. Oh, I see. For some reason, that's not an implicit argument. Okay, what was the... So decidable of if and only if takes a proposition, one implicit and one explicit. Yuck. Okay.
I think you need a prime on the if.
Well, oh, I see, because I'm trying to go, it depends which direction I'm trying to go. There we go. Excellent. Thank you, Keely. The problem was the two decidable of if and only if and decidable of if and only if prime went opposite directions, and I was giving it the wrong thing. Okay. But that one worked, and then, Martin, you had a suggestion.
Yeah, if you using the lemma and then just apply instance as well.
So we probably need to still use the same lambda. Let's see where we are at this point. So we need decidability of evenness. So we can just rewrite using even if and only if even prime. And then we just need decidability according to even of even prime n. And we can write by apply instance. Yep. So that worked as well, except there's a little red squiggle here. What's going on? People, when you're defining instances, people often just leave out the name of the instance because the instances generally won't be referred to by humans. They'll just be inserted into expressions automatically by type class inference. You arguably don't need names for these instances. The problem is Lean's algorithm for naming things, for naming anonymous instances is pretty dull. It just smushes things together. And so this previous instance got given the same anonymous name. So we just have to give this one our own name. Okay. Even that, though, is a little bit dangerous. Because of the way that the type class inference works, it's just going to go and grab, when you ask it to provide instances of something, Lean will just go and grab the first available one it can find. And in different circumstances, it will find different ones. And we saw this, I guess, on question 4, on the discussion around question 4 last time, when we had that annoying commutative semi-ring business making us use funny operations on the natural numbers, or apparently funny operations. So you should often avoid having multiple instances. One thing you can do is just put, I guess I can't put local. I could just make this a definition rather than an instance. And then if I wanted to, in just this file or in this section, use that definition as an instance, I can locally add an attribute. But that then doesn't pollute everyone else, whoever imports the file later, by having multiple instances. Okay. So this was a little digression here on, so a digression on transporting decidability to equivalent statements. Okay. So, yeah, so this was Callum's suggestion that maybe we should, instead of deciding, proving decidability of the first thing we did, we should do decidability of this one. And you could do that, but in some sense it's just pushing the work around. Okay. How might we do this one directly? I mean, how do you know that it's how do we know that it's decidable whether any integer, any natural number is even or not? What's the algorithm? If I hand you 57, what do you do to decide whether it's even or not?
57 modulo 2, and you see if it's 1 or 0.
Okay. Yeah, but that was Callum's answer.
Okay.
That
You look at the last digit.
Oh yeah, you look at the last digit and see if it's multiple 2.
that requires knowing about digits. Digits are complicated. Let's be really dumb here.
Divided by 2? No, I don't know.
Yeah, dividing by 2 doesn't tell you much. Yeah, 37 and 36 both give you 38 when you divide by 2.
1 plus and 1
Yeah, but I mean, deciding evenness and deciding oddness is the same problem.
You can divide by 2 and then multiply by 2 and see if you get the same thing back.
Or you just subtract 2 and see if you end up with 0.
Yeah, so your suggestion was we're going to have to prove lots of auxiliary results about oddness being characterized by that property and so on. But yeah, I think you basically, the really dumbest thing you do is you keep subtracting 2 until you either get a 0 or 1.
Yeah.
You know what the answer is for 0 and 1. What's that?
How's the
Same
difference to
as
modulo 2? Yeah,
taking it 1, 2.
It's exactly the same.
I mean, that's not bad.
Yeah.
I mean, it's literally the same.
Well, okay. Let's
You did what they did.
let's construct two different two different instances of this one that literally does what you want it to do, and one that effectively subtracts 2 over and over again, and then we'll print the terms and see how they look. So I think the version where we do it gorally by hand. Well, first of all, let's desimp even so we can see what we're doing. The idea where you repeatedly subtract 2 is basically that you do induction. So let's do induction on n, and let's call the things we get n and the induction hypothesis. So now we've got a first case where we need to prove that it's decidable whether 2 divides 0, and we were pretty good at that. We did a problem just like that a moment ago. It's true, and let's just use norm num for now, but you could substitute in pretty easily a proof that didn't use norm num if you wanted. And so now we've got the interesting case. So now we've got some natural number, and we know that it's decidable whether 2 divides n. Okay, and our job is to show that it's decidable whether 2 divides n plus 1. But at this point, we can just use our friend cases on the induction hypothesis, because that either says it's not the case that 2 divides n, or it is the case that 2 divides n. Okay? So let's say in the first case, it's not the case that 2 divides n. That means it is the case that 2 divides n plus 1. So we can do apply decidable dot is true. And then our job is to, well, prove something about decidability. Okay.
Can you just say, like, do the predicate again with n minus 2, sorry, n minus 1?
Yeah, I think it, at this point, I don't think that further induction is actually going to help. So, yeah, so at this point, I mean, we just need to have, we've just got some fact here. So maybe let's just prove that as a lemma. You've got some natural number, and you have the fact that it's not the case that 2 divides n. Then you have that 2 divides n plus 1. Okay, that's presumably a provable lemma. And then in this case, we can just now write exact foo n and what was left of the induction hypothesis. And that should finish that goal. And in this case, now we know that 2 divides n, so we have to prove that this case is, well, in this case, we can show that it's false.
And you should just be able to use foo again, I think.
Well, no, you've got to be a little bit careful. It's, I mean, it really isn't foo. It's the converse of foo that we're using here. Okay, so let's sorry that one, but at least okay. So we haven't finished obviously doing. Let's have the same problem. I need to get more names for things. Okay, so we didn't finish building that instance, but we at least reduced it to 2 lemmas that were merely about divisibility. So at least the decidable stuff was out of the way. Yeah, okay, but now let's look at the other version, which was basically proving this version. Okay, so here when we got lucky, and in fact Lean could just provide us with that instance right away. So let's give that one a name, even prime dot decidable pred, and let's see what we actually got there. So let's just print that one and see what actually, oops, copied and pasted incorrectly. This instance that Lean just produced for us using the nmod 2 equals 0 version, what did we get? So, okay, so first of all, well, it's got this annoying id here. Id is just the identity function, which is feels a bit ridiculous that we've defined something with just the identity function applied to something. Why didn't Lean just leave off the id? And this is basically a side effect of having written things in tactic mode here. I think that dsymp there actually caused it to produce the superfluous id. But anyway, so all that this is saying is that actually we're using the fact that that natural numbers have decidable equality. So Lean is using the fact here that nmod 2 actually has an algorithm that is repeatedly subtract 2 until you get either 0 or 1, and then it has an instance of decidable equality. So actually, first of all, we should just ask what is decidable equality. Maybe I should print it. So decidable equality is just that the relationship of equality is decidable, and let's just print decidable rel. That just says that you've got some type, alpha, and you've got some relation on alpha, that is a function from alpha to prop. Then saying that relation is decidable is just saying that for all a and b and alpha, the proposition RAB is decidable. Okay? So I think after you've met decidable pred, decidable rel, and decidable ec, you've met all the relatives of decidability. Okay, so back here, why do the natural numbers have decidable equality? If I give you two natural numbers, what's the algorithm to decide if they're equal or not?
Subtract 1 off each until you get to 0.
Yeah, exactly. Check if both of them are 0. If so, say yes. Otherwise, check if one of them is 0 and one of them is suck of something, in which case say no. Otherwise, they're both suck of something, so remove one suck from each side and go on. So let's check that really is the how it's proved. Decidable ec. And let's jump to the definition. Decidable ec on the natural numbers says, yep, if you've got zeros, it's true. If you've got suck and 0, it's false. Some proof, and so on. Okay?
Why does it need to be suck x? Because it's not. It has to be the successor of something because it's not 0. You know what I mean? Because the first one didn't happen, so it.
Yeah, but I think it.
Makes it more readable.
Yeah, for one, it's clearer what the cases are. But I think here, I suspect something would go horribly wrong. Let's try it.
What proof they gave the last one? Like suck X or whatever.
I have to open that to get anywhere here. Oh dear. Maximum class instance resolution depth has been reached.
What does that mean? That was happening a lot during the assignment.
That is always sad. Okay, so let's postpone that question just 1 second for when we talk about how type class resolution is actually happening. But yeah, usually what happens is that instead of the space of all possible instances being a tree, some loops have formed, and Lean is spinning around and around in some loop in this graph that it's searching to try and find an instance for you. So let's maybe just make it def. Still unhappy. Ugh. Okay, maybe let's not do this digression for now. Okay, let's back up. Okay, let me just claim that the instance of decidable equality was basically the algorithm that we talked about. So yeah, but it is a little interesting why this nmod 2 version managed to be so easy. And the point was that rather than talking about evenness as some arbitrary predicate on natural numbers, about 2 dividing it, we actually just said, well, there's this function that you can apply that's got an algorithm that you can apply to n, and then after that it's just testing equality. Testing equality is nice and easy. Okay. What else do I want to say here? Let's maybe look at MathLib's, or one of MathLib's proofs that that being prime is decidable. So this is an instance up here you can see of decidable prime p for any p. And the instance that's defined here is exactly one of these decidable of if and only ifs that we were using earlier. So presumably what's going on here is that prime underscore def underscore less than prime is just some statement that being prime is equivalent to this condition. So let's check that. Sorry. Prime def lt. So that statement, ignore everything after the colon equals, it just says, yeah, p is prime if and only if p is bigger than 2, and for all m, 2 is less than or equal to m, implies that if m is less than p, then it's not the case that m divides p. Great. So when we go back and look at this definition, decidable of if and only if needed a few things. What did it need? It needed some proposition that's meant to be equivalent to our proposition prime p. It's got to have a proof that that proposition really is true if and only if the one we started with is. But then there's secretly, remember, an implicit argument. Decidable of if and only if takes this other proposition b, the proof of equivalence of a and b, and an instance saying decidable b. Okay? So what we should worry about when we see this line, the definition of decidable prime 1, was where on earth it's getting the instance of all of that stuff from. Okay? That's magically being provided by the type class inference process. But we can investigate this. We can just copy and paste that whole thing. Fine, my keyboard doesn't work. Okay. And we can... Oops. Copy and paste definitely didn't work. Sorry. Copying and pasting from this window seems very unreliable. There we go. Okay. So we can ask if Lean can show that that is decidable, but it doesn't know what this p is we're talking about. So let's tell it p is an actual number. And then let's just hope for the best and write by apply instance. Lean says, sure, I can find an instance that does that for you. And now we can inspect what instance it actually found. So let's define that to be inst1, and let's print inst1. And what has it said? It said, oh, I can just use and.decidable. So what might you guess and.decidable is?
Well, make sure both sides of that.
Yeah, so and.decidable is this instance that, given propositions p and q, a witness that P is decidable and a witness that Q is decidable gives you the instance that P and Q is decidable. Okay? And you could, you could read the definition here, but it's kind of I think everyone could probably fill in that proof now themselves. If P and Q are decidable, it's not so hard to work out the truth of P and Q. Okay, so we can now just keep working our way down. Well, except we can't, because, well, I guess we can actually, because we know what the two sides of the AND are here. So why don't we keep looking at those guys? So we'll define inst2 to just be the decidability of P is greater than 2. Okay, and again, apply instance works, so we can ask it, how did you do that? And it says that what it used was, it's got a decidability instance for the relationship less than. Okay, it can decide whether one natural number is strictly less than another one. Maybe that's not the most interesting one, so let's look at the other branch of the AND for a moment. This is this one. And again, apply instance just works fine, so we can ask what did that do? And something pretty interesting happened there. Okay. This is definitely the interesting step. So it's used some instance nat.decidable low high. Can anyone have a guess? What? Yeah, exactly. It's saying that if you've got some predicate on the natural numbers, for example, it's not the case that that m divides p, and that happens to be decidable for a fixed value of m, and it's decidable for all p, then it's also decidable if you think about m ranking over some finite range of possible values. So let's have a look at what it actually says. Nat.decidable low high. And so that says if you've got some bounds low and high, and you've got some predicate on the natural numbers, and that predicate is a decidable predicate, then it's decidable. Then the statement for all x between low and high, p of x is decidable. Okay, and there's some proof here which we could look at if we wanted to, but let's not for a moment. But again, you can imagine how that one might be constructed. Well, I don't know. Is that one that we should look into further, or should we? Continue on chasing the primality stuff. Okay, let's stay on the main thread for a moment and see what else we get. So what were the inputs to this this decidable low high? Well, the secret input was just this one, the fact that the predicate that we're testing for each value of x was actually decidable. And in our case, that's just this one. It's not the case that that p divides m. Okay? So we can look up, we can see how Lean manages to establish that instance. So now we've got two natural numbers, p and m, and we want to know that it's decidable whether it's not the case that m divides p again, we can look inside whatever it managed to do there. This step was actually not that exciting. It's just got an instance that says if some some proposition is decidable, not that proposition is also decidable. So the next thing we're meant to look at is to work out how it did this without the not. Print that to see what it came up with. And it's got some statement that divisibility in the natural numbers is decidable. And finally we can print that to see what it's doing. Maybe? Did I get the name wrong? Sorry. Of course, decidable DVD, not DVD decidable. Okay, what's going on here? Well, it's actually saying here that divisibility is decidable because A divides B is true if and only if B mod A is 0, and finally we've got decidable equality in the natural numbers. So at the end of the day, it boiled down to the suggestion of using mod. Okay, so the kind of amazing thing in all of this is that it was really just done for us. At least once we got to this level, once we'd said P is a prime if and only this condition, apply instance was doing all of the work after that in relatively sensible ways. I mean, we were using the fact that you can put together instances using and not. There was this more complicated one using low-high, and then there was finally this one about divisibility being decidable because equality is decidable. You can test this condition. So what actually happens when we ask it to do type class resolution? Maybe let's go back to one of these early ones and we can watch it happen. So, I mean, we sort of watched it happen by hand here, by slowly unpacking the definitions and printing them and seeing which instances were produced. But you can turn on some tracing to watch the process. Kelly, do you remember the syntax here to turn on? It's going to be trace.something, set option trace.class instances. Okay. Okay, and as soon as we turn that on, some green squiggles appear all over the place. And each of these green squiggles is representing some place where Lean has gone away and used type class inference to find an instance that we've asked for. You might have thought there'd just be one green squiggle for the apply instance, but there are lots of green squiggles. Why is that?
Because the signs are overloaded.
Yeah, exactly. Every one of these operators, these less thans and divide symbols and so on, are generating a type class inference search. If we hover over this one maybe, it's saying that it's gone looking for an instance of has divide for the natural numbers. And you can actually scroll down here and find how it did that. So to read these traces is a little bit confusing, but the first number is the depth, and it's just doing a very naive depth-first search of some tree of possible instances. So it says, okay, what I know I need is an instances of has divide, of has divide on the natural numbers. And its first guess is that one way that you could do that is, well, there's a function, com semi-ring has divide, which says that anytime you've got an instance of com semi-ring, you can extract from that an instance of has divide. So then it goes away and looks for an instance of com semi-ring. How do I get this up here? There we go. Then it goes away and looks for an instance of com semi-ring natural numbers. And for some reason, it considers the possibility, why don't I try rat.com semiring? And it says, no, that's a terrible idea. That's an instance of the rational numbers being a commutative semiring, and not an instance of the natural numbers being a commutative semiring, so we'll give up on that. And so we're still at level 1 because we gave up on one branch of the search. And now it says, oh, I'm looking for a commutative semiring, and I've got this function that says every canonically ordered commutative semiring gives me a commutative semiring. Why don't I try that? Sure, seems reasonable. So now we're one level deeper in the type class search, and it says my job is to find an instance of canonically ordered commutative semiring on the natural numbers. And it says, oh, one way to do this is this crazy thing, with top. Who knows what that is? But it says, no, that's not going to work. It can prove that branch of the search won't give it what it's after. And so we're still at level 2, and it says, oh, why don't I try this function, nat.canonically ordered commutative semiring. And the fact that the trace stops here is an indication that it succeeded. And so you've now got to sort of unwind back through the chain of successful choices to see that we constructed an instance of has DVD natural numbers by producing this instance, converting it to an instance of just commutative semiring, and then converting that to an instance of just has divide. Okay. So that's going on everywhere where you're using any of these overloaded symbols. Has less than is going off, and notice actually it tries a bunch of dumb things. Like it considers the possibility of using the fact that string has a less than operation on it. Before a few steps later on, it manages to realize that there's an instance of nat.has less than, and it should use that. So there's a bunch of interesting stuff going on under the hood here. You can see that because type class inference happens all over the place, it has to be very fast, or we would die, get bogged down in these searches. So a lot of stuff is actually cached, and these searches only happen once. And perhaps later we'll have to learn how to deal with breaking that cache when we need to. One thing that you'll might run into is that if you're in a begin-end block and you create a new instance, like you just define one using a have statement, for example, in the next couple of lines of the proof, Lean will refuse to use that instance that you just created because the instance is already cached and it's not going to accept the new one. But there's a trick to say, please rebuild the cache. And we can basically write have capital I instead of have. A lot of the tactics have a version with a capital I appended on the end, which says do this and then rebuild the instance cache. But we'll come to that if we need it. Okay. But the thing that we were most interested in was this one. I think. Oh dear.
Whoa.
Okay. So this message here, this green squiggle on this line, multiple instance searches are going on, and we actually have to dig through a bit to find the one we want. First of all, it goes off looking for a has-bind tactic. That's something to do with interpreting the word by in this line. It's trying to work out, what we're even doing.
And you can overload it if you want
And you can overload it if you want to, and Keely has done some of these scary things at times. So you can make by mean other things
do whatever you want.
than run a tactic. But let's carefully avoid looking at monad tactic for now. That can come in a couple of weeks. And we can see that this is the one we're interested in, where it's looking for decidability of this AND statement. And if you look here, it tries a whole bunch of things, and they're all dumb, and they all get rejected with failed isdefec. So you scroll down, and you can sort of tell where to scroll down to, because you can see we're still looking at level 0 of this search. So you can just scroll all the way down, and down, and down, and down, and
It's a really
down.
little sidebar thing.
Yep, okay, let's speed up. And you go all the way down, keeping an eye on those zeros to see if one of them eventually turns into a 1. Oh, one of them turned into a 1. Okay, so what happened at that point? It said, well, one way of providing a decidability instance is to use and.decidable. And Lean said, oh yeah, that does actually match. It's possible that and dot decidable with some mysterious arguments, x 407 through 410, could possibly produce something like this. But then it works out, well, if and decidable with some arguments is going to produce this, x 409 is going to have to be a decidability instance for p is greater than or equal to 2. And that's what's going on here. We're trying to solve the type class problem. Can I find some value of x 409 that gives me an instance of decidable p greater than 2? And so it goes off.
And try to use the ones we find in the file first.
Yeah. So this is actually a good question. You can set priorities of instances, and it checks the ones with higher priorities first. But you can notice that it's not entirely here just that ones in the file had higher priorities, because these first four we all defined right now. We also defined quux right now in this file, but has divide.decidable is just something from the library. So it's in between. I suspect this is actually a good question, how you inspect what the priorities of those guys are. I suspect they all just have the default priority, and there's some internal tie-breaking mechanism that I don't know about. We can maybe, here's a trick. No, that's not telling us any information about the instance priority. When we print those statements, it tells us that they're both labeled as instances, which just means that Lean will try and use those definitions in type class search.
If you change it though, it should appear as an attribute.
Okay, yeah, so let's go back up to quux. Where was quux? All the way back here at the beginning. And set the priority. Keely?
At priority and the number.
At priority.
The default is 1000.
50. Great. Okay, and so now if we print quux, you'll see that not only is it marked as an instance, it's marked with priority 50. Okay. So the default is 1000.
And higher is better.
And higher is better, meaning we try that first.
Yep.
Okay, great. So this one actually, setting quux to 50, should mean that in that type class search that we were just doing down below, where we saw quux was like the 6th line that it tried, we should see that that's disappeared now because it's much lower priority. So let's actually go and check that, which involves scrolling a million miles down this trace until we find a 1. There are the 1s. And sure enough, quux has disappeared from the list there. It used to be number 6 just after has decidable, but it's now dropped off the list. And of course, because Lean is doing just a depth first search of possible instances here, probably it'll never even try that quux now, because some other branch of the search will have succeeded and found something. Okay, so we go down here a bit. We're still trying to prove decidability of p greater than or equal to 2.
And maybe it's worth saying if you have like a non-open-ended instance, like just prime n is decidable, and you have 2 of those, one is lower priority, it will just never be tried.
Yeah. Oh, I see. You mean if you've got 2 instances that give the exact same,
And the
that have
search
the same
couldn't try to
type.
continue past it.
Yeah. Okay, so this one eventually solved the constraint decidable p greater than or equal to 2 using decidable less than, which was the one that we saw it using earlier. So that explains why up in one of these earlier print statements we saw that coming in. So now it turns to another branch of the search. It has to find a decidability instance for the other side of the and this is the one that should hopefully produce the nat nat low high decidable instance. And we can scroll down here. And indeed, there it is. It found nat decidable low high. But of course, remember, nat decidable low high itself required another instance. That fourth argument of nat decidable low high was an instance saying that the predicate inside there is actually decidable, and that's what Lean is going off and trying to solve now as a new part of the search. And it succeeds a moment later by using, hopefully using decidable.not, which is what we saw. There it is. It's succeeded with decidable.not. So now it's at depth 3 in the search, and it's trying to prove decidability of A divides P. And it finds that. And finally, everything's finished. All the sub-goals that were produced in the search are all filled in, and it stopped. So, what are some things to know? There's absolutely no reason why this sort of search can't have loops. You can write instances that require other instances, which might try and use the original instance.
Maybe have a go.
Ah, okay.
Oh,
Achilles, put me on the spot.
Oh, no,
Okay,
it
let's
doesn't have-
let's do one. Yeah.
I didn't
Okay.
mean you, but
So how might we do this? We could. So let's define a really boring class.
I have a way to come up with a natural number, but it needs a natural number already.
Yeah. How do we do that with instances?
Oh,
Do we have to make natural numbers a class? I think we do to do it with an act. So you might have noticed that there's this keyword class, and sometimes we're writing instance instead of definition. So Lean will only. Oh, are you about to tell me it's just going to do it anyway?
can
Let's try it. Let's try and produce a natural number by apply instance. See what it says. Okay. And it says, I tried. Oh, no, it says I didn't even try. So the target is not a type class. So it is checking that the thing you're trying to produce an instance of has been marked with this class attribute. But we can do that. We can probably write local attribute
that
class
definitely works. Yeah.
nat.
Need some more square brackets around the
oh.
class.
Class. Valid.
If you maybe try replacing with nat.
No way. Oh, I'm so upset. Why did it work for nat and not for? Okay. Anyway.
The only reason I had that idea is because I wrote nat and it worked.
Okay. So let's turn off tracing so we can just see the error messages more easily for a moment. So now what does it say? It says failed to generate an instance for nat. Okay, there are no instances out there that provide natural numbers. Okay, that's fine. So Keely's suggestion then is we just define an instance. Let's call it f, that takes a natural number as an implicit argument and produces a natural number. Let's give that guy a name, and it just spits out x again. Okay, this is a really dumb example of a loop. It tries to produce a natural number. This is an instance that provides a natural number, but demands that you give it a natural number to start with. And hopefully now we'll see this spiral off to infinity. And indeed, it gives us a different error message. Maximum class instance resolution depth has been reached. The limit can be increased by setting an option. And sometimes that's a valid thing to do, but usually it's a sign that your type class inference is poorly designed. Someone's given you crappy instances that cause loops. Is there anything you want to add about instances? Any questions about what on earth is going on at the moment? Maybe we could, let's fix this problem. Let's let's do it below so we can still see it happening.
But there are some interesting potential problems that could happen right now.
Let's give it, just quickly, let me do this. Let's give it a higher priority instance, G, a natural number, which says, no, the answer is 42. And then this one works just fine. And this example, if you check, well, maybe let's... Oh, is foo already defined? I'm running out of metasyntactic variables. Preprint bar. It in fact says G, but G was 42. Okay. So this higher priority meant that it never got into this infinite loop and used this instance instead. Okay. But sorry, Kelly, you were...
No, well, I thought you might have done it on purpose here. Maybe I just, like, maybe, you know, if you didn't change the priority,
Yep.
It's somehow a toss-up whether it'll work or not. And if you think...
Oh, I see. If I just do this, this same instance. I see.
And if it's lower priority, I presume, even though there's a perfectly good instance sitting there, we'll still exceed the maximum depth just trying out over and over.
So let's try it again where I've defined that instance but just at default priority. And curiously, this one did work. So somehow G prime beat out F, even though they were at the same priority. But that's not really in your hands. That's just an implementation detail there. Okay, maybe I'll get rid of those. Yeah, any other? Okay, so obviously the question about decidable predicates for primes, I mean, you can by now give a lame answer to at least the first part, constructed an instance, basically by repeating what we saw was going on here in this type class inference here. But the question does also ask you to give two different instances of decidability. Yeah, so... Okay, what does that even mean? Does someone have a suggestion as to what I have in mind for one being better than the other?
I mean, you could check every number less than n, or you could just check the ones less than square root n. Whatever.
Yeah, or even intermediate between those, you could check all the numbers up to n over 2 or something. And square root n is maybe getting kind of complicated. You've got to prove something about square roots, but stopping halfway is a reasonable thing to do.
You could only check primes less than n.
Yeah.
Although it would depend on how fast you can find those primes as to whether it's better.
Yeah, yep. So I mean, any of those I'd say is better, but I think you should carefully choose the better to make your life as easy as possible. So I think actually Isabel's suggestion is actually probably quite complicated because you need to prove that if something is not prime, then there is a smaller number that is prime that divides it, and that's, I mean, obviously that's there in MATLAB and is not that hard. But if you're trying to do that step with your bare hands, that's extra work. The other thing that you might even consider is when you're trying to make one instance and then you're asked to make an instance that's better. A good solution to this is to take to make sure your first instance is really bad. Just saying.
Prime is prime if it's a number. That's my
No.
first instance.
It's got to be good. It's got to be the correct definition of prime, and it really does have to be a decidability instance. But maybe you can check something.
So another question about this, you say like do not simply use an existing instance from MATLAB. What I assume what you mean by that is like if we define prime is like that for all statement there.
Yeah.
We can't just say like by a play instance.
Yeah. So I think I do want to leave this a little bit of a gray area. I mean, I don't want to completely forbid you from using any decidability instances that are already in MATLAB because it's a bit dumb to have to write the one that says that if P is decidable, not P is decidable, and if P and Q are both decidable, P and Q is decidable. So maybe I'll sort of leave it up to you where you which decidability instances of mathlib you already use. Any that are sort of basic logic ones, go for it. And any that feel like they're really about prime numbers already, do those ones yourself. It's maybe but yeah, I'll leave that up to you guys.
Okay. So I've got a sort of a separate question about
Yeah.
how they define the complex number.